Hello, and welcome to AMAT362, Probability for Statistics at UAlbany. This is lecture 17. Today's lecture is going to be slightly different, as I've already pre-written out the notes and only add annotations as we go through. So it's going to be a little bit quicker, but that's because part of this is just going to be me talking and trying to motivate a sort of philosophical concept. We'll get into some more detailed examples at the end of the lecture. So today is our first genuine introduction to continuous random variables. This is sort of the counterpart of discrete probability, but where outcomes lie in some continuous, technically uncountable range of possibilities. This actually makes a lot of sense because if you think like things like height and weight, or even time, these are things that naturally vary in a continuum, rather than something like in the binomial distribution, where you count the number of successes, which always has to be an integer. So just to highlight the difference for discrete probability, we can talk about the probability of individual outcomes. Now this is very nice because then if I want to know if my probability of a range of outcomes, I can just sum the individual probabilities. Let's go ahead and go through a familiar example. So suppose I am here on my skateboard. I've got my trucks and my wheels, and I'm trying to do a kickflip. I'm going to lie to you. I'm going to say that I can actually land a kickflip 1 out of 5 times. In reality, it's much lower. What's the probability that after 10 tries, so I've tried 10 times, I managed to land 2 kickflips? All right, this is a classic example of a binomial random variable. I have a fixed number of tries, and I want to count the number of successes. The number of tries is n, the probability of success is p, and the number of successes is k. So I just need to plug into my formula with n equals 10, p equals 1/5, and k equals 2. When I do that, I get roughly 30%. Now, let's try to look at a small variation of this concept. Suppose I just scale up the number of tries, but I keep the expected number of outcomes to be about the same. Notice that I chose 2 in part because 1/5 of 10 is 2. So I'm just asking, what's the probability of actually landing the exact expected number of times? Again, counter to what you might think, it's not 50% or even 100%. In this case, it's 30%. So let's repeat this and say, what if I try 100 times and I want to know what's the probability of 20 successes? So notice I've just multiplied all the numbers in the first version of this problem by 10. So if I were to use my binomial formula, I would say, all right, this is binomial with n equals 100. K is still 1/5, but now p equals 20. Notice that when I do this calculation, I get a lower number. In particular, it's gone from 30% as being the probability of landing the expected number of times, which is 2, to 9% of a probability of landing the expected number of times, which is 20, because 20 is 1/5 of 100. And I can repeat this process. So let's imagine that I instead try 1,000 times and I ask for 200 successes. It's still the same proportion of successes, but the probability goes down to 3%. You just plug this into your calculator, or honestly, you'll probably need to use a special formula either built into your calculator, or you can just go to a website and Google binomial distribution calculator. And that's what I did to get that number. Because in all honesty, if you actually work out how to compute 1,000 choose 200, it's going to be pretty large. And the only reason why that number becomes something that's less than 1 is because it's attenuated by these huge numbers, 4 to the 5th to the 800 and 1/5 to the 200. Or I should say huge exponents, which then become very, very small because I'm raising a number less than 1 to a really high power. So the question is, what's going on here? Why is it going from 30% to 9% to 3%? And notice that roughly the reduction in each step is about a third. Go from 30 to 9. A third of 30 would be about 10. And a third of 9 is 3. So can you explain this pattern? Well, let's call back to a result from lecture 15. It's 2 lectures ago. This is where I introduced this notion of the pointwise central limit theorem. And again, what we're trying to estimate is what's the probability that the number of successes, well, let's just say that a sum of independently distributed, identically distributed random variables equals some fixed value. Assuming that the distribution for each of these xn looks something like it takes a certain range of integers as possible values. So this could be Bernoulli, which is the case here. Did I land the kickflip or not? 0 or 1. Or it could be a uniform distribution. Let's say I roll a die and I want to ask what's the sum of rolling my die 100 times, and I get exactly the value, 200. In the case where you apply this formula, when this is Bernoulli, where each of the xi's are Bernoulli, then you know the sum is binomially distributed. Only in that case can you make this n times mu the same thing as n times p, because mu equals p for a Bernoulli random variable. That says that the average of a Bernoulli is just the probability of success, which makes sense. And then additionally, sigma for a Bernoulli is the square root of p times q. And so you can see that, again, this factor which appears in the central limit theorem, when I do square root of n over sigma squared, which would be p times q. Do I get the formula from what I call the baby central limit theorem? Anyhow, let's go ahead and use this approximation to go ahead and calculate it. And let's look first in a situation where actually the central limit theorem, or even the pointwise central limit theorem, doesn't work so well. Namely, when we're looking at fairly low numbers, like 10 tries. Nevertheless, if we try to do that, let me go ahead and just warn that this is a not so good approximation. Let's go ahead and figure out exactly what this value here is. So I'm going to take phi of 0, and this is little phi. So in particular, it looks like e to the, so let's go ahead and plug it in. So phi of 0 is going to equal 1 over the square root of 2 pi times e to the minus 0 squared over 2. Of course, e to the 0 is the same thing as 1. So what I'm looking at now is just 1 over the square root of 2 pi. All right, so let's go ahead and I'm just going to plug this into my calculator here. So I'm going to look at 1 over the square root of, then I'm going to take 2 times pi times 10 times probability of success, which is 0.2, times the probability of failure, which is 0.8. So notice that for this calculation right here, I actually get about 31.5%. Notice earlier I said about 30%. So this is actually a pretty good approximation, even when the numbers were low, like just 10 tries. Let's go ahead and run through this calculation. But now in the case where I'm trying 100 times and I'm asking what's the probability of succeeding 20 times, which again is the expected number. So what do I need to do differently this time? I still have 1 over the square root of 2 pi. Times 100 times 1/5 times 4/5. So I'm just going to change my 10 to 100 in my online calculator here. So notice this works out to be about 9.97%. So this is for n equals 10, And then for n equals 100, I get 9.97%. And then finally, if we just repeat this calculation for 1,000, we get that this ends up equaling exactly what I said earlier, which is 3.15%. And this corresponds to n equals 1,000. Now, if you look carefully, what's the ratio of each of these values? You'll see that it's decreasing by the ratio of something like the square root of 100 divided by the square root of 10, which is the square root of 10, which ends up being about 3. And then I could do the same thing. Well, now what's the ratio between probability of 2 successes out of 10 versus 200 successes out of 200? It ends up becoming something like square root of 1,000 divided by square root of 10. And so that ratio ends up being, again, closer to about 100, which actually makes perfect sense, because when I take 31.5 and I move this over 1 decimal place, I end up getting my 3.15%. So what we're seeing is that in general, by virtue of this dividing by the square root of n times sigma squared factor, as n gets large, so meaning as n goes to infinity, the probability of success is going to go to 0, which is exactly what I say here. Now, this might feel a little counterintuitive because, obviously there's some chance of doing that, but you should also intuit that because the range of possibilities is larger, the probability of equaling a specific number becomes smaller. And so I try to summarize that with this sort of philosophical takeaway, which says that for large data sets, or you can think of this as a large number of samples or draws from a distribution, talking about individual probabilities of individual outcomes becomes increasingly meaningless. And by that, I just mean that it tends closer and closer to 0. And we know that really we're still studying the same fundamental distribution, but in having more data shouldn't somehow make our results less accurate or less meaningful. Instead, what we need to do is we need to sort of pivot to a situation where instead of looking at the probability of individual outcomes, which is what we do with discrete probability, we look at the probability of ranges of outcomes. So how would that work in this example here? So how do we talk about ranges of events? So, and this is going to be the key idea. When we move from discrete to continuous probability, you no longer want to think about the probability of points. You don't ever talk about just the probability of 2. You talk about some window of possibilities or range of possibilities. And so now what we want to do is sort of interpret or rescale our units in such a way that even though the number of draws or samples increases, the window remains of a fixed size. So what does that mean to keep the size of this window fixed, even though n is getting larger and larger? Well, this goes back to really what was the meaning behind the z-value computation that we did through both the baby central limit theorem and the sort of grown-up central limit theorem. So we had to compute z-values. What is a z-value? A z-value is just asking how many standard deviations from the mean are you? So to be concrete, in this case, I'm looking at, instead of asking what's the probability of me landing 2 kickflips out of 10 tries, let's give myself a little bit of wiggle room and say, what's the probability of landing between 1 and 3 inclusive? So I'm including 2, but I'm also including the possibility of 1 and 3. Now, of course, we've already observed that 2 is going to be n times p. That's my expectation of my binomial. And so when I'm looking at, well, maybe I can go up to 3. When I compute the z-value associated to 3, what I do is I take 3 minus 2, and I divide by the standard deviation of Sn, my binomial, which is the square root of npq. When I do that, I see that talking about plus or minus 1 kickflip, which is sort of my natural units when I'm doing these sort of small samples, what I'm really talking about is plus or minus 0.79 standard deviations. Now, this is an important concept to turn to, because instead of talking about raw numbers of kickflips, I could talk about just a fixed number of standard deviations. And so as my standard deviations change, which we all know is now going according to this square root of n times pq, and so this will change as n changes, I can keep that sort of ratio constant. So explicitly, what ratio am I keeping constant? So if I say, what's the probability of landing between 1 and 3 kickflips? The question I should ask when I change the number of attempts, the number of tries, to 100, is I want to ask, well, what deviation x above the mean, which is 20, gives me this same number? This is my 0.79. So I'm trying to solve for x, where if I look at now the ratio of the standard deviations coming from 100 trials with the standard number of standard deviations coming from 10 trials, which is, n, where n equals 10, then I can just solve that, like, actually, when I take this and I put it on top here, you'll notice that all these factors cancel. And then what I'm left with is x is the square root of 10. So that tells me now that I've increased the number of tries by a factor of 10. And so my window of possibilities should go up by the square root of 10. We kind of referred to this maybe in passing when we talked about the sort of square root law when we're doing the law of averages, which is essentially that uncertainty propagates as something like the square root of n. Or when we're doing sort of empirical averages, it ends up being like 1 over that. So to summarize, when I'm looking at 10 tries and I want to ask for a range of possibilities that corresponds to plus or minus 1 kickflips, to keep this question sort of scale free, and that means invariant under increasing n, I should say, when I have n equals 100, then instead of asking for plus or minus 1 kickflip, I should ask for plus or minus 3.3 kickflips. All right, because it's not an integer, it doesn't feel quite as meaningful, but at least it scales more appropriately. So then the question would be like, oh, what's the probability that he lands between 16 and 24 if I like round up? And that would be the better analog of the probability of landing between 1 and 2 kickflips when I'm only trying 10 times. Correspondingly, if I'm making a single kickflip my sort of unit of measurement, which comes out of trying it 10 times, when I consider 1,000 attempts, now the proper question, instead of asking what's the probability of, say 200 kickflips, which is 20% of 1,000, plus or minus 1, instead I need to ask, well, plus or minus 1 standard deviation. And 1 standard deviation in this case corresponds to 10, because the square root of the ratio of 0.79 standard deviations, or 0.79 standard deviations for 1,000 tries ends up working out to being plus or minus 10 kickflips. So you'll see we went from 1 when n equals 10 to 10 when n was equal to 1,000. Now, all of these, when you now rephrase this question, are going to end up having essentially equal probabilities. And that just comes from the fact that when I use my z-table, I'm going to end up just computing, all right, what is phi, capital phi of 0.79? So I could just go ahead and write this. So the probability of being below 0.79 sigma and above by 0.79 sigma, that probability is going to turn out to be something like capital phi of 0.79 minus capital phi of minus 0.79, which if you remember is the same thing as 2 times the capital phi of 0.79 minus 1. And so if I go to my z table and I look at um, 0.79, it's this last entry right over here, 0.79, that's 7852, 0.7852. This is equals 2 times 0.7852 minus 1, which if I go ahead and put into the calculator here, 2 times 0.7851 minus 1. This ends up actually being closer to 57%. And that probability is now scale free because I've adjusted my language to reflect sort of the underlying units, which corresponds to the number of kickflips that I'm actually trying. So this is me just trying to motivate that at the end of the day, what we're really interested in for these kinds of experiments is, here's my number of attempts or a number of successes, sorry. But standardized by the average and then divided by the mean, at the end of the day, these all end up looking something like this normal distribution. And now the probability all ends up being equal to this area under the curve. And so just by making my units or my question reflect how many times I'm actually trying, I now have reduced to integrating this function between two values, which ends up being invariant or sort of scale free after I do this sort of Z transform. Now, the thing I want to highlight is that's not the only way in which we approach it, continuous probability. It's just a very surprising way, which comes out of starting with very discrete things and then using this sort of miracle known as the central limit theorem to approach this question of how do I actually talk about reasonable ranges of results? And why is that actually like the right thing to talk about when I'm looking at situations with large data or large number of tries? Let's go ahead and look at some other examples where these sort of random experiments work. But I first want to lay out sort of a dictionary between the discrete and the continuous. And so this is going to be our dictionary. Actually, I'll back that up. So this is a dictionary. So previously, when we were talking about discrete distributions, you could draw the PMF table. So you just basically draw the PMF table. As a histogram. And so what we've got drawn here, and this comes from this is from Pittman. What we've got here are these sort of blocks, which we just sort of take as the probability of these individual outcomes. And in this setting, we're thinking of these, each X here as having some integer possibility, number of successes, or the number of tries or something like that. But when we kind of scale and we take number of successes minus the mean, divide by this funny thing involving the square root, we end up then creating a distribution of values which lies in a sort of more continuous range, things that vary by decimal places and are not integers. And in that case, if we kind of start to bend possibilities in terms of some width, based on the number of standard deviations, then what we start to see is sort of a blocky approximation to a continuous curve, which with the central limit theorem, what we're looking at is something that looks like this e to the minus c squared over 2 divided by square root of 2 pi. And we'll see why that square root of 2 pi comes from in just a little bit. But now instead of drawing this PMF table, we can't really represent a continuous probability using a table. Instead, we just need to define what's called now, so the PMF is now going to be replaced with the PDF. And here the D refers to density. And so now we have to just draw the PDF, because we can't write it down as a table. That would involve specifying a probability for individual outcomes. And those are going to be essentially 0. Now the way in which you want to think of probabilities, you want to think of probability as asking, to what extent does it lie in a range, where my range is indexed by some little window. And so this then you think of as the probability density, which is roughly the probability per unit length of values near x, where x is whatever thing we're looking at. Here we were looking at 20. So now we're going to look at 20 plus some, some small amount. So here you don't really want to talk about pointwise probabilities as much, because really it's going to be the integral of a function over a small window. And if that window size is very small, that integral is going to also be small. Now, when we talked about interval probability and discrete probability, what we did is we basically summed up certain blocks. So if I wanted to know, say, the probability between A and B, what I was going to do is ask for the area of these of the sum of these blocks. But now what I can do, because I have this continuous approximation, is I can just take the integral of this function of the PDF. So I integrate the PDF to then get area under the curve. And here, area is going to be our analog of probability. Now, of course, for all of these notions to cohere with the axioms of probability that are introduced at the very beginning of class, they need to satisfy some certain basic intuitive properties. So first of all, we require that with normal probability mass functions, the probability is always non-negative. Negative probability makes no sense. And moreover, we need to satisfy this normalization axiom. So here, this right here looks like the normalization axiom. But now it's going to end up looking like, take the integral and make sure it sums up to 1, or that integral equals 1. But luckily with this formalism, everything goes through as we have been talking about it with discrete functions. But now we're just replacing sums with integrals. So essentially sums become integrals. And if you remember back to calculus, that's actually how we defined integration. It was a limiting process of taking sums of smaller and smaller triangles. It's the Riemann integral. And so wherever you saw a summation sign in discrete probability, just place it with an integration sign for continuous probability. And now you can make things make sense. Like, for example, the expectation of x we defined as the sum of x times the probability that capital X equals that little value x. But now, if I just apply this rule of turn a sum into an integral, I can now say that the expected value of a continuous random variable is just the integral from x of the PDF. And sometimes we just use f instead of little p. to emphasize that this is a continuous density. Now, I've tried to motivate in this lecture and also the sort of second third of the course, and now we're in the final third of the course, as a way of approximating discrete probabilities using continuous ones. And so that came about most significantly, in the case of the binomial, where we had essentially the baby central limit theorem. And then in parentheses, when we use any sum, this is the grown-up central limit theorem. And that process took us to the study of area under the curve of a normal distribution. Now, one of the reasons why we didn't have to do much integration in that part of the course was because actually integrating this phi function defined up here is really difficult. In fact, it's impossible to do using elementary methods. But with other settings where the involved function for modeling the process using a continuous random variable, sometimes the integral actually becomes tractable. Now we're back into doing and practicing our skills from calculus. So today we're going to focus on two things. First of all, we know how like the uniform random variable, which normally would model, let's say, sums, so like roll a die. Now it's going to go to something like throw a dart and look at its horizontal position. That's a situation which might be modeled by a uniform random variable. It might not, but we can start just with the assumption that it is. We'll go through that and we'll show how some of these quantities, such as the expectation, which is the integral of x times the density, how that is calculated for the uniform distribution on a continuous interval. And then we'll end with this sort of analog that takes geometric, or even you could think of this as Poisson in this sense, and how that takes us to this new random variable, which we've not met yet, which is the exponential. So let's go ahead and just spend what's left in our lecture going over just these two continuous random variables. All right, so we're starting with the uniform. So one way you can think of the uniform distribution is, imagine I'm throwing at a dartboard, and here's the bullseye, but I'm just interested in how I'm doing in terms of relative displacement to the left or right of the bullseye, and not actually like, am I landing in the bullseye, which would involve taking this third or this second axis. That's essentially going to lead to the study of the uniform distribution for two variables or in two dimensions. But right now, let's just start with one dimension. So I throw my dart. Here's my dart. And then I record its x position. That's the horizontal position of the dart using Cartesian coordinates. So the way we evaluate probabilities in continuous probability is I need to ask, well, what's the probability that I lie in a range, let's say between little x and little y? Well, so for the uniform distribution, you want to think of probability as being proportional to relative length. So here the relative length is actually going to be the width of the dartboard. And again, this assumes I always hit the dartboard. I'm saying essentially that there's no possibility that I might not hit the dartboard, which for some people, that might be more likely than not. So since I'm saying probability is proportional to relative length, what I just need to do is compare the length of this versus the length of the overall window. Of course, if I ask, well, what's the probability I land in the window? Then I see sort of my something has to happen axiom at work, because in that case, what's the probability that x lies between a and b? Well, that just ends up equaling the relative length of b minus a over b minus a, which equals 1. This is just saying I have to land, something has to happen. But now if I take a smaller window, well, obviously the smaller and tighter, the lower the probability. And you can in fact see that if I set x to equal y here, then I'm going to get 0, which gives us also this counterintuitive fact that the probability of a single event equals 0. And this is a situation where that happens for purely geometric reasons, rather than when I started the lecture and I talked about, well, it happens for reasons because of this pointwise central limit theorem, which decreases values by 1/square root of n. So to summarize, the uniform probability distribution on A to B, it doesn't matter if you use closed or open interval, because again, the probability of a point ends up being the same, ends up being 0. So the PDF, the probability density, is 1/b minus a if x is inside that range and it's 0 otherwise. Now, how might you compute something like, where's the expected location of my dart? So if I apply the definition, well, I need to take the value x times the probability density of x, and I need to integrate it over all possible values, which is from A to B. I could have thought of this as an integral over all of r, or an integral from minus infinity to infinity, but that ends up equaling the same thing because the function is 0 outside of that. Anyhow, I can pull out, because this is a constant, and now I'm just integrating x. Luckily, that's an easy integral to do. It's x squared divided by 2. That's the antiderivative of x. So now I have x squared divided by 2. I evaluate it at the endpoints b and a, and I get b squared minus a squared. But then I have divided by 2, because that came from this anti-differentiation process. And then I had this normalizing factor, which is the length of that interval, a to b, b minus a. Now, if you remember, b minus a squared actually factors as b plus a times b minus a. And so luckily, these factors cancel out. And we get actually the intuitive formula for the mean, which again says that if I've got, let's say, this block of probability from A to B, and let me use black for the axis. And so again, I've got, so this is 1/b minus a. Then I've got a situation where the balance point is right in the middle, which makes intuitive sense. That's the balance point, that's the midpoint. Now, how might I compute something like the variance? Well, remember, the way to compute the variance is to use our handy formula, which says that the variance of x is the same thing as the expectation of x squared, which is the random variable where I take x and then I square the value. And then I take that from what's actually the mean of x squared. I've already computed the mean of x, so it's easy to square. It's right here. So let's compute the expectation of x squared. That just amounts to, all right, you take the integral of x squared times the probability density function from A to B. Again, this, because it's a constant inside that window, that constant right there, can factor out. And so now I just need to integrate x squared over my window of possibilities, which is A to B. Again, polynomials are easy to integrate because I can just raise the degree and then divide by that new raised degree. In this case, I get x cubed divided by 3, evaluated at b and a, which means I look at b cubed minus a cubed divided by 3, which comes from that factor right there. And then, of course, I've got my minus b minus a, which comes from the normalizing factor. Now I'm going to do a little algebra, because this can actually simplify. B minus a cubed turns out to be the same thing as b minus a times b squared plus ab plus a squared. Why is that true? Well, if I look at it over here, I can just recall that if I multiply this out, I get, all right, b times b squared is b cubed. B times b squared is b cubed. B times ab is ab squared. B times a squared is ba squared. And now I'll do the same thing for a. Minus a times b squared gives me minus ab squared. Minus a times b squared gives me minus minus a times ab gives me a squared b. And then minus a times a squared gives me minus a cubed. Luckily, some things cancel. That cancels, that cancels, that cancels. And I'm left with the b cubed minus a cubed I promised. Again, this is handy because now I can cancel out these factors. And so to finish the calculation, I can say, all right, expectation of x squared, it's also called the second moment. Is given by the formula I just wrote there. So now to compute the variance, I need to take the second moment and subtract it by the first moment with the square. So again, I do some algebra, things collapse, and I end up getting this variance of x is b minus a squared divided by 12. Now let's compare that with the variance of rolling a 6-sided die. There, what I had to do is look at 6 minus 1 plus 1, which just ends up giving me 6 squared, minus 1 divided by 12. These formulas actually look very similar. And in some sense, actually, the continuous formula is more elegant because it doesn't deal with the fact that, oh, the possibilities only occur at integer spacings between a and b, which is what happens here in the discrete variable. But notice everything else is the same. You're still subtracting by something, got a 12 in the denominator, and so on and so forth. So we'll do some examples of this in class where we can get down and practice these computations. Let's say one more random variable. This is a really important one because we're going to spend a lot of time then deriving other distributions that come from this. So the exponential random variable is a really good random variable for monitoring things that have like have some sort of decay process, like a radioactive ion or something like that. It also just does a good job of modeling waiting time. Suppose I'm waiting in a line at a restaurant or a fast food restaurant. What's the expected amount of time before I get served, and what's the probability of seeing some deviation from that? That question is completely governed by the exponential random variable. So this governs decay, lifetime, and waiting times. So it's extremely powerful. But just to give you a definition, we say that a continuous random variable t, think of time, is exponentially distributed with parameter lambda if its probability density function is f of t, which is lambda times e to the minus lambda t, t greater than or equal to 0. And it's 0 otherwise. Now, lambda has to be given to you, or it's given to you in sort of a disguised form. One way in which lambda is given to you for these kinds of problems is by giving you what the expected time is, or expected decay time, or expected wait time. So often you're given this, which is 1 over lambda, which you can then invert to find lambda. And then you're ready to solve the problem and do things the ordinary integral way. Let me show you an example where this occurs. So suppose a piece of equipment, and we can think of this as like a light bulb, for example, has a lifetime that's exponentially distributed. And moreover, we're told that this average lifetime is 100 working hours, or let's say 100 hours on. Old incandescent bulbs, like this was actually not like an unreasonable assumption. Bulbs would like, pop or have something go wrong all the time. So having 100 working hours out of an old-fashioned light bulb is actually not too crazy. So that's the information. So here you're in secret given the expectation of T, the expected lifetime, the average lifetime. So we now know that lambda is going to be 1 over 100. But now let's look at the question again. It says, what's the probability that this light bulb lasts more than 200 hours? So again, now we're replacing sums with integrals. So the question is, what's the probability that T is greater than 200? Well, what I need to do is just integrate my PDF. Again, I can think of the graph of my PDF. I've got this. This is my graph of lambda e to the minus lambda t, or this is the time axis. And now I'm asking, well, what's the probability of 200 hours or more of working time? And you can imagine that that's sort of the balance point, or where my expectation is for this might be somewhere around here. That's my balance point. So I need to compute the area under the curve to the right of 200. So I just have to integrate from 200 to positive infinity of lambda e to the minus lambda t, where lambda is given by this. So luckily, exponentials are very easy to integrate. And moreover, we've already got the lambda factor, which would come down when we differentiate e to the minus lambda t. If I take the derivative ddt of this, I'll end up getting a minus lambda that comes down. But I've already got lambda here. I just need to account for that minus sign, which goes away because there's probabilities are obviously positive. So this is the definite integral value of this integral. I've taken the antiderivative of this, which is this, and then I've put the endpoints here and here. All right, well, obviously e to the minus infinity, we can just see that as this goes out to infinity, e to the minus lambda t goes to 0. So this factor goes to 0. So then we're all only left with what was on the left hand or lower hand limit here, which was 200. Now I need to multiply by lambda. Lambda is 1 over 100. And so I end up getting e to the minus 2. So that's our answer. But let's take a second to reflect where else this number might come from. So remember, if you want to really ballpark something, you could say, all right, my lifetime of my light bulb is 100 hours. So I can also think of this as a process where, I'm chunking into hours, and every hour I'm just asking, does it fail or not? Maybe a reasonable thing to say is like, well, if my average lifetime is 100, maybe the probability of failure in any given hour is 1 over 100. So then this question of turning this into a discrete probability question, where I ask, what's the probability of no failures in the first 200 hours? Well, that means I need to take the probability of not failing, which is 1 minus p, and I need to raise that to the 200th power. Now, if we use this sort of small approximation, this Taylor approximation to e to the minus x, e to the minus p, I can think of 1 minus p as being roughly equal to e to the minus p. Now, this is nice because I can then just use my exponential function instead of sort of taking this, typing in, raised to the 200. But if I do that, I can then say, all right, e to the minus p raised to the 200 is just taking 200 times p in the exponent, where p is 1 over 100. So this looks like e to the minus 200 divided by 100, which is e to the minus 2. So suddenly, this exponential distribution feels a lot like what might be just a continuous approximation of this sort of Poisson or geometric process, where I'm looking for the probability of, let's say, no failures. All right, so that's it for today. We're going to do a lot more examples in class, and I look forward to seeing you soon.